Hi, everybody. This is Miss Wiesen, and this is the second podcast of Unit 5 over chemical kinetics. We are at the top of page 4, and in today's podcast, we're going to start learning about the different types of reaction rates. Now, before we begin, I'm going to ask that maybe you jot this down, and you're going to see these in the notes, of course, but when we talk about rates and rate laws in chemistry, we can think about them in kind of several different scenarios. We can determine the rate instantaneously. You can determine a relative rate. And then later in this unit, we're going to learn about the differential rate law and the integrated rate law. So these are just 4 general ways of how we can think about rates when it comes to chemical reactions in chemistry. And so remember, as a quick review, what is a reaction rate? So the rate of a chemical reaction is going to be measured by the decrease in concentration of reactants or an increase in the concentration of products. Does that make sense? Generally speaking, you guys, if you look at reactants, that's the things we're going to start with. And if we actually start at time 0, right at the beginning of a chemical reaction, don't you agree that we have 100% of the reactants? And as soon as we hit the start button, if you will, we start to have product formation. So generally speaking, as reactants decrease in concentration, products are going to simultaneously increase, okay? And so when a reactant decreases, we'll generally get some type of negative value when we do instantaneous rate. And when you do an increase in the concentration of products, you're going to get a positive value. Now, you will see that here in just a second with our calculations. What you're ultimately going to do in this particular case, one way to think about rate is instantaneously. And you're going to think about it in terms of a change in the concentration of the species you're talking about divided by an interval of time. In other words, right here, the change in the concentration of the reactants divided by time. So you probably have already learned this in previous science or math classes, but when you see that delta, that means change in, right? And so when you go to calculate the change in something, you always need to take the final value and subtract it from the initial value, okay? So final minus initial, rather. And then you're going to divide that by an increment of time, okay? And so if we do an example here in our notes, instantaneous reaction rate is simply put the rate at a very given instant of time, which is kind of why it's named that. Now, you probably, again, if you've had pre-calc or calculus, you know how to do this. It's okay to show off. Let's do a quick example here. What you're going to ultimately do is you're going to need to have some graphical information in front of you to do this. And you're going to take the slope of a line tangent to the curve at a particular time frame. All right. And you want to be particular with regards to your vocabulary when you're describing this process. So if on a test question you were asked, to describe how you would take the instantaneous rate, you don't want to just say, take the tangent. That's not going to earn you any points. You need to be explicit and clear that you are going to indeed take the slope of a line tangent to a curve. Let's do an example. Now, again, you need some type of graphical data to do this type of rate. And you can see here the pictorial is showing us that the beakers up at the top of this chart here are showing us that we're starting with, at time 0, we're starting with 50 molecules of the reactant, which is in purple. And of course, because the reaction hasn't started yet, we should technically have 0 molecules of the product at that very exact time. Now, once the reaction starts to proceed, and as time goes by, you can see here, and I'm going to annotate it with, the highlighter, the concentration of the reactants decreases, and simultaneously, the concentration of the products starts to increase, right? Hopefully that makes sense. Now, if we are trying to figure out the instantaneous rate at a particular time frame, what you're going to do in this example, it wants us to find the instantaneous rate of this reaction between 10 and 20 seconds. Okay, and it wants us to do this first for the reactants, and you can see it says it right there. So for the reactants between 10 and 20 seconds, what's the instantaneous rate that this reaction is occurring? And so you got to be very clear when you're looking at this table, which of these lines, again, is the reactants. And we just said it was the purple line. That's because as time goes by, concentration of the products is going to decrease, as you can see. Now it wants us to do it between the 10 and 20 second mark. So I'm going to go ahead and take a slope of the line tangent to the curve between the 10-second mark and the 20-second mark. Sorry, you guys, my line might not be so incredibly straight here. Okay, there we go. There's my slope of the line tangent to the curve. And I already know that rate is going to equal, in this case, a change in concentration of the reactants divided by time. And remember, change in, okay, that delta is final minus initial. So what you need to do here is go over to your graph and analyze some data and pull some data out here. I'm going to, with another color, go at time seconds and kind of dot over to my y-axis, and I can then get a concentration or the number of molecules at 10 seconds. And then I can do the same thing and kind of dot on over here at 20 seconds to see how the number of molecules have changed. And so over here, I'm just going to kind of, take that data and plug it into my to my formula here. So my concentration initially at 10 seconds, you guys, I'm going to call that about 24, more or less. You might call it 23, but let's just go with 24. The concentration 10 seconds later, so concentration final, that's why I put an F there. I'm going to go ahead and call that 10. So it looks like there's 10 molecules after 10 seconds has passed. It definitely decreased. And it looks like the time increment here, well, we had 20 seconds minus 10 seconds. So it happened in a 10-second time interval. And therefore, let's go ahead and plug and chug. Rate equals 10 final minus initial. And by the way, I'm just going to put brackets there. And our time increment was 10 seconds. You guys, if we're doing brackets and concentration, that's molarity. So don't forget that's moles per liter. That's what we're assuming here, even though it's telling us the number of molecules. But anyway, you do this calculation and you will notice that you'll get a negative 1.4. And the correct unit here, if we're using molarity, would be ms minus 1. Does that make sense? So our rate in between the 10 and 20 second interval is a negative 1.4 molarity over seconds. Okay, it's asking us also to do the same thing now to calculate the instantaneous rate for the products at the very same time interval. So again, if I kind of just draw a slope of line tangent to the curve here on the product line, you will also see here another scenario where you would need to kind of dot over and get your values, get your Y values or your concentrations. And again, let's go ahead, and we know rate is going to be equal to the concentration of the products, the change in concentration of the products rather, over a time frame. And let's go ahead and analyze the data table to find out what that concentration initial was. I'm coming over here, you guys. I'm going to call that 26. And 10 seconds later, I'm going to call the final concentration 40. And then, of course, our time frame, again, was 20 seconds minus 10 seconds. It's a 10-second interval, right? Same thing as before. So let's calculate our rate here. Our rate would be our final minus our initial. And again, brackets indicate molarity. So that's what we're going to make the over and over again, just make the assumption that when we do these rate calculations, molarity is what we're going to be using for concentration. So 10 seconds. When you do the calculations on your calculator or in your head, you're going to get a positive 1.4 molarity over seconds. Okay. Now, obviously, the rate here looks constant within that time frame. But make a note. Let's go ahead and just add it over here that I want to mention that rate is not necessarily constant. It can actually change with time. So you might see that pop up. Anyway, so ultimately calculating an instantaneous rate, you see the formula you're going to use. Rate equals a change in the concentration of the species you're interested in divided by time. Draw a slope of the line tangent to the curve, analyze the data set using the graph, and get your answers. And so lastly, before we learn about relative reaction rate, I wanted to ask what happened to this system at 60 seconds? yes, you're going to need to go back and look at your data. And I want you to practice determining the instantaneous rates for substances at 20 minutes. And actually, this, you guys, is supposed to say seconds. I apologize. These are supposed to say seconds. So why don't you get some practice and maybe go and do some different time intervals to see if you can get the rate of the reaction when you've got a nice curve there, not when it's flattened out or the rate of the reaction completes, okay? Because what you start to notice is after the 60 seconds, when you get here to the right-hand side of the graph, notice this curve kind of flattens out, and it's asking why, and that's because the reaction comes to completion, okay? So that's your instantaneous rate. Let's talk about relative reaction rates. And relative reaction rates are expressed as the change in concentration of a reactant per unit time. So just like before, so you should focus either on the disappearance of a reactant or the appearance of a product. And again, you're going to get different values for your answer. You'll either get a negative value or a positive value depending on what you're focusing on. But like I just said, oftentimes in chemistry, they'll focus on the disappearance of reactants and not so much the products, although you might see it. So the word relative here does not refer to your family member. It refers to terms that relate to each other in the context of a system, in this case of a chemical reaction system. So the simplest way to obtain a relative reaction rate, or a relative rate expression is another way to say it, is to place a 1 over each coefficient in the balanced equation. So yes, you are going to need a balanced chemical equation to do and to get the relative reaction rate. Now remember, if there is no coefficient in front of a chemical species, it is implied that it is a 1. All right, so you are also going to need to apply the correct algebraic sign. So you'll use a positive sign for products, and you will use a negative sign for reactants. Do you remember why? I mentioned it just above an instantaneous rate. It's negative for reactants because those are disappearing with time. And it's positive for products because they are appearing over time. So let's go ahead, and I have two examples here in our notes, two different reactions. As you can see, and as I just mentioned, you need a balanced chemical reaction. So it's telling us above, the simplest way to obtain the rate is to place a 1 over each coefficient in the balanced chemical reaction. So let's take a look at this first one. You see that this is a coefficient of 2. I just circled it. So you would say a negative 1 over 2. And I'm going to set up the expression. Okay, that was the relative rate expression for the reactant in this particular reaction. Now you're going to have to do it to the whole reaction. So set that equals 2. And remember, when products are forming, you're going to use a positive value. And again, the coefficient in front of this oxygen is a 1, you guys. So I'm not going to even bother. So I'm going to write the expression for this one as the change in concentration of oxygen over a change in time. And then let's go ahead and set that equal to the last product. You see that there's a 2 coefficient, so it'd be positive 1 over 2. So you essentially are creating fractions here, and you're taking the change in concentration of NO over a change in time, a time frame. Okay, so this is how you would write the relative rate expression for any particular reaction. Again, one more time, making sure it's a negative value for your reactants and a positive value for your products, and simply taking the coefficient from the balanced reaction and putting a 1 over whatever that coefficient is. Okay, now if you want to get rid of those fractions, you certainly can. How would you do that? Well, you can get rid of these pesky fractions by multiplying by the least common denominator. But you guys, I would embrace fractions. They're not as scary. Most of you probably don't mind them. But anyway, if I wanted to get rid of fractions, I could just multiply this entire reaction by 2. And when I do that, I'll go ahead and down here, rewrite them, and I would get the following. Okay, so that would be the simplified relative rate expression. Now, if I really actually wanted to find out numbers here, I would have to be given the data, the concentration change data of the species in the reaction. I would have to be given the time intervals, and all those things would be given to you. But if you are indeed doing a relative reaction rate, this is generally how you would set it up. Again, one more time, you need a balanced chemical reaction to do the relative rate. Let's try this again and follow the same process. Go ahead and pause me. And for example number 2, go ahead and set up the relative rate expression for examples 2 balanced chemical equation. Okay, here's the general rate expression for example number 2. Again, put me on pause. Go ahead and get rid of those fractions. What would be the least common denominator here? How can we get rid of those fractions? Put me on pause and see if you get the same answer as me. All right, so here is the simplified relative rate expression for the second example. Okay, so once you know how to set these up, you could just, again, take the data that's given to you in a particular problem and plug in those values. Let's do exercise 1 here. It's asking us to write the relative rates of change in concentration of the products and reactants in the decomposition of nitrosyl chloride, which we write as NOCl. You guys, you can see that I put the expression here. Again, note that right now you're not doing any calculations, but you're just setting up the rate expression. And again, you would need to be given some data, some concentration and time data, and plug and chug. All right, I'm hoping that those are 2 relatively simple ways to represent rate in chemical kinetics. We are going to move to something a little bit more complex in the next podcast, but ultimately that is all for now, and thank you so much for watching. Bye-bye.